Hello, this is Mrs. Johnson. This is MAT221, Calculus 1. We're in section 4.8, which talks about antiderivatives. So in Unit 5, which is 4.8 is the first section in Unit 5, we start thinking backwards. We start thinking about if we are given a derivative curve, can we go backwards to the original curve? Now, we started thinking about this when we started graphically looking at this in section 4.4, when we looked at a graph of a derivative and then answered questions about the actual original function f of x. So now we're going to pursue this a little bit further analytically and using algebra values and shortcuts that we did for the derivative. We're now going to do those same shortcuts backwards. So why do we study antiderivatives? We do this because often we're given a rate of change curve and we want to answer questions about the original curve or the curve it came from. For instance, a physicist who knew the velocity of a particle and might wish to know its position at a given time, or an engineer who can measure the variable rate of which water is leaking from a tank and wants to know the amount leaked over a certain amount of time. This particular example, by the way, what happened just recently, well, relatively recently, when the Darkwater Horizon, a oil rig out in the Gulf of Mexico several years ago, had an explosion, and BP had oil leaking into the Gulf of Mexico, and they knew the rate at which the oil was leaking out into the Gulf, and they knew the time it started and they knew the time they capped it. So they used calculus and they used these ideas of antiderivatives to figure out just about how much oil had actually leaked into the Gulf. And then they made BP try to get as much of that as they could and recover as many, make sure they recovered as much of that oil as they could. Another example would be a biologist who knows the rate at which the bacteria population is increasing and might want to deduce what size the population will be at some future time. These are all STEM or science and technology and mathematical applications to looking at an antiderivative. So in each case, the problem is to find a function that Leibniz and Newton called capital F, whose derivative is known as the given function f. In other words, if we're given a function and we know it's a derivative function, what is the family it came from? What is the function it came from? The father of that function, kind of, the capital F function. If such a function, capital F, exists, it's called an antiderivative of f. Now, one of the reasons why many students can get confused here because of the mathematical notation, antiderivatives were actually discovered first. Integration or integral calculus, which is what we're going to start studying now, was actually discovered first by Leibniz and Newton. They looked at rates of change curves and called them f. They hadn't had the notation yet for f prime and so forth. So they used just the function f as the given function, which was a velocity function or a rate of change function or a derivative function. And they used capital F to signify the function that given function, which is a derivative, came from. That function at which that given function came from. So sometimes the notations can get a little bit tricky here, but we'll try to always solidify in our head that when we're talking about a function that's given and the function given is a rate of change function, we'll always want to think backwards to the antiderivative function that we can signify, in this case, by capital F. So here's the definition. A function capital F is called the antiderivative of a given function f on an interval I if we know that capital F prime is equal to little f. In other words, little f is the derivative function of some other function that we're calling capital F for all x in the given interval. So we have introduced the idea of antiderivatives, and we learned how to sketch the graph of an antiderivative in section 4.4 if we're given the graph of the derivative. Now we want to know the differentiation formulas that are in a position to find the explicit expressions for the antiderivative. So what we want to do now is we actually want to find the formulas, knowing that what we know about differentiation formulas, to be able to go backwards analytically or algebraically or from a function notation. How can we go backwards to this antiderivative function? Not just graphically, but also analytically or algebraically. So let's start with a little bit of a review. If I said to you f of x is equal to 2x plus 3, you could easily find the derivative of that function is equal to 2x. So if I gave you a function 2x, you could say, well, the function it came from is x squared plus 3. However, there's a little bit of a dilemma, because if I gave you the function y equals x squared minus 5, its derivative would also be 2x. So you can see we have a little bit of a dilemma, but not that much of a dilemma. Going backwards, if you notice, if we're given a derivative function and the derivative was 2x, notice both of these functions could possibly be the antiderivative function, or the function whose derivative is given as 2x. So this is a little bit of a dilemma for us. So what do we do here? Well, we notice that both of these functions are only different by the constant that's involved. Notice the curve itself is x squared, but the only difference between the two functions is the constant that I add on or subtract from. And because when we take a derivative, that constant disappears, it's very likely that both of them have the same derivative. They do have the same derivative. However, when we reverse the operation, we have to say, okay, the antiderivative function is x squared, but there might perhaps have been a constant attached to the function that we don't know what it is, because when we took the derivative of the function, the constant dropped away. So we'll notice here that our given antiderivative, this is called the general antiderivative, is actually the family of functions that all look alike. They are x squared plus perhaps some constant c. This also makes sense to us graphically. If you think, if I said graph the derivative of this function, it would graph 2x. If I said graph the derivative of this function, it would graph 2x. So notice if we're given the derivative function and want to go backwards, we say, okay, when we reverse the operation, we can reverse the x squared and make it, the 2x and make it x squared. We know that the derivative of x squared is equal to 2x, but each of these functions could have possibly had a constant. We don't know what that constant is, so we just put in c in this answer to remind us that there might have been a constant attached to the function that gave us the derivative 2x. So we'll notice here when we take antiderivatives, these are called general antiderivatives. They are also called the integral or the indefinite integral, which is the general antiderivative of this function. When we take that general antiderivative, our answer is a function, and it's a family of functions that all just differ by a constant. Any one of these functions, x squared plus 3, x squared minus 5, x squared plus 100, x squared minus 52, all could have a derivative of 2x. So our answer is the family of functions, all that have this general formula, y equals x squared plus perhaps some constant. Now, if we had some more information about the antiderivative function, we could actually find what that value of c is. For instance, if I said to you, I know that the derivative of a function is 2x, and I also know that the original function has a point on it that when x equals 1, y equals 4. Find the one equation, not the family of functions, not the general antiderivative, but the one equation that will have a derivative of 2x and will also pass through the point 1, 4. I find that general antiderivative first, and then I place 4 in for y when x equals 1, so I can actually solve for that value of c. So the one and only one function that has a derivative of 2x, but also passes through the point 1, 4, is the function y equals x squared plus 3, where I can actually solve for the value of c. These type of problems are called initial value problems. That's because we're given some initial value on the original curve where we can actually solve for the constant. Any equation that we deal with containing a derivative is called a differential equation. Now, we talked about this earlier in the semester when we talked about differentials and we talked about differential equations. So if you're given something that starts with a derivative, for in this case, y prime equals 2x, this is a differential equation because it's an equation containing a derivative. It becomes an initial value problem when you're also given, in this case, an initial condition, and we're asked to find the original equation. So this is called a differential equation. Any equation that has a derivative in it, and we see it, the derivative is there. And it becomes an initial value problem when we have more information where we can actually solve for the value of c and not just give the general antiderivative. All right, let's look at some other things here as we start to try to go backwards with our antiderivatives. Now, in the next video, we'll be talking about more of these antiderivatives, but for right now, let's look at x squared. It isn't too difficult to discover that an antiderivative of f if you think of the power rule in mind. Now, we know that if the derivative is x squared, right, we knew that it must have come from x to the third by our derivative formulas. But there was no 3 in front of this formula here. So there must have been a 1/3 coefficient in front of the function to bring us to a derivative of x squared. So if we have a derivative of x squared, it must have come from 1/3 x to the third. When I take the derivative, you notice 3 times 1/3 would be just 1, which gives me the 1 coefficient I want here in the derivative. And then I subtract 1 from the exponent to get x squared. So we have a theorem 1 here in in section 4.8 that says, if capital F is the antiderivative of little f on the interval I, then the most general antiderivative of f on this interval is capital F of x plus c, where c is some arbitrary constant. Notice that the antiderivatives are the family of functions, all that have a derivative of x squared. If you think of all of these functions, look at all these functions. They're the family of functions, but if you took the derivative of every single one, what would you get? What's the derivative of this function? That would be 1/3 times 3x squared, the 3's cancel, plus 0. So the derivative is x squared. The derivative is x squared. The derivative is x squared. The derivative is x squared, and so forth. Notice this gives us the general antiderivative, which gives us the family of functions, all that have the derivative of x squared. So let's stop the video for now. I'll stop this video for now and start our next one. And we'll talk about more general antiderivatives.